All right, hey Chem students. This is part one of a three-part review on equilibrium. Remember, you guys have a test on Friday, so I'm going to go over this. So the first section, 19.1, is the nature of equilibrium. I will be covering three different components of this section. The first part is how to write a generic equilibrium constant equation. Then part two is solving it, and then part three of this section is going to be solving for an unknown concentration. So in the first step, you'll notice that I have a sample equation right here. This is taken straight out of the reading. And then in order to set up an equilibrium constant, you'll need to, one, make sure you have a balanced chemical equation, and two, you'll need to know what a coefficient is. So a coefficient is a number in front of a chemical in a chemical equation that determines the number of moles of that chemical needed. So essentially, to set up an equilibrium constant, your KEQ is your equilibrium constant, and you're going to put the concentrations. That's what these brackets are right here. You'll notice, you see them there. Brackets mean concentration. So you need the concentration of your products on top, and then the exponents that you notice here and here are the coefficients that you will need. If it's a 1, you don't need to really raise it by any power. So that's just a general overview. So in my example right here, I have phosphorus pentachloride, and it's going to decompose into phosphorus trichloride and chlorine gas. So to write the equilibrium constant, you would just write KEQ. Again, there are no values for this because this is just how to write the equilibrium constant. In the next part, I'll show you how to plug in the numbers. So you take your products. So you need to reverse this. So this will need to be reversed. As you notice, I actually put this in here this way so that I can go over it. So you'll notice that what most students do is they will put the reactants on top and the products on the bottom, but you actually have to do it the other way around. So essentially what you need to do is you need to put these ones on the top, and then these ones need to go on the bottom. Just like that. And so what you'll have is the concentration of phosphorus trichloride multiplied by the concentration of chlorine gas. You don't raise them to any power since there are no coefficients. You'll notice here and here there's no coefficient. And then on the bottom you put the reactant, which is the phosphorus pentachloride, which is going to decompose. So that's the first part of this. Moving on. Part 2 of section 19.1 has you solve for this. So I'm going to use a different equation. So here is my equation right here. It's highlighted. You'll notice that it's hydrogen gas and chlorine gas, when combined, make hydrochloric acid. So what you're given is you're given a few things. One is that it is at equilibrium, which means we can solve for the equilibrium constant. It gives you a value for temperature. Not really that big of a deal, but it's just good to know that it is at equilibrium at a specific temperature. You're given the concentration of hydrochloric acid. You're also given the concentration of hydrogen and chlorine gas, and they're actually equal to each other. So the first thing you'll want to do is write out your equation. So KEQ, and then just like we wrote up before on the other equation, you'll want to write it out this way, where you have your products on top. So here's your product, and you'll notice on this one, you have a coefficient of 2. So that means you will raise the concentration of hydrochloric acid to 2, to the power of 2. On the denominator, you'll notice that you have the two reactants. So you have hydrogen and you have chlorine concentrations multiplied by each other. So then you will write the concentrations themselves inside the brackets. So if you look up here, the concentration of hydrochloric acid is 0.0625 molar. So you would write that in there. You'll notice I wrote it in there already. And then you raise it to the power of 2. The 2 comes from the balanced chemical equation here. also write the concentrations of both hydrochloric acid, hydrogen gas and the chlorine gas. So you'll notice the hydrogen gas I wrote here and the chlorine gas I wrote here. So once you plug those numbers in, what I've found is that if you use Desmos, I'm sure a lot of you use it in math, it makes it a little bit easier because you can actually just copy and paste this into that and it'll solve it for you. But you can also use a calculator. When you solve for this, you'll notice that you get a value of 1.93 times 10 to the 2. So one thing to note, and this is from a previous section, but there are no units for the equilibrium constant. That is because the 2 molarities on the top and the bottom, they cancel out. Then you'll also want to remember what a value that's greater than 1 versus a value that's less than 1 means. So a value that's greater than 1 favors the products, which means that this reaction favors the products. So if you take hydrogen gas and chlorine gas, mix them together, it's going to favor making hydrochloric acid. But the reverse reaction, so if you were to put the concentrations and you were to take this and flip it, then you would notice that your KEQ would be less than 1. So that means that the reactants would be favored. So in this case, just make sure that you understand what a equilibrium constant greater than 1 and equilibrium constant less than 1 means. Moving on to the last little bit, this is solving one of the problems that was homework last week. So I'm going to use it as my example. So you have nitrogen monoxide combines with chlorine at 400 degrees Celsius to form nitrous cell chloride in the following reaction. So you have 2 moles of nitrogen monoxide plus chlorine gas makes your nitrous cell chloride. Your equilibrium constant is given to you, so as 28.1, which means, again, it's greater than 1, so this is favored. And then it's at 400 degrees. That it has reached equilibrium, so in a certain reaction, a quantity of nitrous cell chloride has allowed to decompose in 400 degrees until equilibrium is reached. So you're given the concentration of NO. That's why you have these brackets here. And it's given as 9.4 times 10 to the negative 3 molar. And then you want to find the concentration of chlorine gas and nitrous cell. So a couple of things you want to ask yourself in these kind of problems. And again, just to review real quick, this type of problem is to solve for unknown concentrations. And I know some of you students had questions on this. So first question you should ask yourself is, what is the question asking me? So it's usually in the last part of the question, but I highlighted it here and I put it in quotes. It says, find the concentration, that's what the brackets are, concentrations of chlorine and concentrations of nitrous cell. So what do we know? So here's what we do know. We know that we have a chemical equation that's balanced. We also know what the KEQ is, equilibrium constant. We know the concentration of nitrogen monoxide. And we also know something interesting from the equation. So if you look at the equation, for every 2 moles of nitrogen monoxide, you only need 1 mole of chlorine gas. So that's what I wrote here. Why is that going to help us? Well, you'll see in a minute. So before we set up the problem, we have to do something. If the ratio of moles for nitrogen monoxide and chlorine is 2 to 1, then the ratio of the concentrations at equilibrium for nitrogen and chlorine has to be 2 to 1. Or if I write it as the concentrations of nitrogen monoxide, which is what I'm given, I will take my concentration of nitrogen monoxide and I need to divide it by 2 to find the concentration of chlorine. Remember, you only need half the amount of chlorine for a full amount of nitrogen monoxide. Okay, so knowing that, I already solved then for the concentration of chlorine gas. And since I solved for the concentration of chlorine gas, now there's only one more item to solve for. Remember, just going back up here, it says, what is it asking for? It's asking us to find the concentration of chlorine gas. I just did. and now just the concentration of nitrosyl chloride. So moving on, I'm going to set up my equilibrium equation. So equilibrium constant equals, remember so just the way you set it up, you have your reactants on the top, the reactants on the bottom, and you have the products on top, and you have two coefficients. So I need to go back to my equation up here. I have a 2 in front of nitrogen monoxide and a 2 in front of nitrosyl chloride. So I write it just like this, the concentration of nitrosyl chloride squared divided by the concentration of nitrogen monoxide squared multiplied by the concentration of chloride. So then I just plug in my numbers. So down here, I've kind of showed the breakdown of it. So 28.1, that was the given equilibrium constant. The concentration of nitrogen monoxide was given as 9.4 times 10 to the negative 3. I wrote it out as a decimal, and then you square that, multiplied by the concentration of chlorine, which I solved up here earlier. Oops, solved up here. I move my denominator. I multiply both the numbers to the other side. So you'll notice I put it here, and that leaves me with the concentration of nitrosyl chloride squared. So then I need to find the square root of that value. When I do that, I find the following numbers. I find that my concentration of nitrosyl chloride becomes 3.4 times 10 to the negative 3. And I do need to put units for this, and the units are m for molar. So all concentrations have a unit of molar. Molar means moles per 1 liter. So then I just need to plug in my concentrations for NO and Cl. And again, it was only asking us for these two, but I like to put all the concentrations just so that I can see all of them there. And that's how you solve for unknown concentrations, given a specific amount of concentrations and the equilibrium constant. And that wraps up the section 19.1 review.